So I just wanted to give a bit of an update. Metal Earth actually helped support a postdoc that helped us get our LA-ICPMS sulfur isotope method up and running. So I just wanted to give an update about where we're at by measuring sulfur isotopes by LA-ICPMS and combining that with trace element mapping in pyrites. And so this is a bit of a group effort. Metal Earth helped support, partially supported Guillaume Barret during his postdoc. He's now at the GSC in Quebec. And I'll be showing some work from various students that are working in the Val d'Or area. You guys all know Mitchie. He's now published his 3 papers and is working for Nutrien. But Bruno Caldabella, who's been part of Metal Earth in the past, and François Xavier Bonnet and Giovanni Pedemonte, who are working in the Val d'Or camp, but not on Metal Earth projects, but Metal Earth associated, I guess. And I also want to highlight our research group at Université Laval. We're a big group called the Chaire en Exploration Minérale, and of course, other co-authors as well. So how is gold transported in fluids? We've been talking a lot about collecting sulfur isotope data, but why is it important? So gold in auriferous fluids is thought to be transported by hydrogen sulfide complexes. This is because the fluid is near neutral, it has low salinity, and is generally at temperatures of less than 400 degrees Celsius. So this is the perfect conditions to transport gold with sulfur ligands. And this is really apparent in many deposits. We often see gold associate with sulfides, like this example at the Hermes Prospect in Western Australia, where you have quartz carbonate veins, arsenopyrite, and free gold. But gold can also be refractory in sulfides or hosted as inclusions. I heard Francois talk about the Canal Belle deposit earlier today. This is an example of arsenian pyrite at the Canal Belle deposit. It has weight % arsenic in it. You can see with nanosims imaging the lattice-bound arsenic in the pyrites, as well as nano-inclusions of arsenopyrite. And you also see that gold is refractory in these pyrites, occurring as lattice-bound or as nano-inclusions. So to make the point that gold and sulfur are often intimately linked. So we think that if we better understand the source of sulfur, we can better understand the source of gold in orogenic gold deposits. But there's still many theories about where sulfur is sourced from, and where fluids and gold are sourced from for orogenic gold deposits. The major consensus recently, though, is that metamorphism of either sedimentary basins or mafic crust are the main suppliers of sulfur, gold, and fluids to orogenic gold deposits, based on, kind of the paper that came out in 2022 by Goldfarb and Pitcairn. And so, because of this metamorphic model, people have been going recently into the Pontiac, and we'll see lots of talks after the break about the gold fluid window. So whether the Pontiac and other metasedimentary provinces in the Superior Craton can act as basins that provide fluids, gold, and sulfur to be remobilized into orogenic gold deposits, and if the conditions were perfect to release them all at the same time. And I just wanted to highlight as a side note, this is a new paper that came out in 2025, and what we did in the Pontiac was not look to understand if the Pontiac was a source of sulfur, but we wanted to see across metamorphic gradients the pyrite to pyrrhotite devolatilization reaction and measure its multiple sulfur isotope signatures to demonstrate that H2S that's being released as pyrite devolatilizes to pyrrhotite will have the same signature as that original pyrite. So there won't be much fractionation in sulfur isotope space. So that's recently put out. It has a Merck or a Metal Earth number, which should make Ross happy. Okay, so that's maybe where sulfur is sourced, but what we want to do is more go look at the orogenic gold deposits and understand their sulfur isotope signature to compare with all the work that's being done in gold fluid window and other places to understand if these sulfur isotope signatures are being preserved in orogenic gold deposits that can indicate their source of sulfur. So sulfur isotopes are complex. They have very fractionated systems. This is because they occur in the atmosphere. Sulfur can have an oxidation state of +6. But it can also exist in really reduced state, and so it can go into the geosphere as H2S. So it can form many different types of molecules. This gives it a signature that we can trace through different reactions. And we think that different reservoirs have different sulfur isotope signatures. So, for instance, seawater today is very heavy, whereas basaltic magma would have a sulfur isotope signature of about 0. And the sedimentary rock record can be very varied, and this changes over time as well. But sulfur isotopes are a bit more complicated when we're talking about precipitating pyrite from a fluid. We have to think about, in that fluid, what is the pyrite species? So for instance, in seawater, sulfur is sulfate. In a basaltic magma, it can be SO2. And in the sedimentary rock record, it's usually, in the Archean at least, as pyrite. So if you precipitate pyrite from a fluid that has quite a bit of oxygen in it and sulfate, in that case, you will have a very large fractionation factor down to -25 at temperatures that are typical of orogenic gold fluids. And if you precipitate pyrite from a fluid rich in SO2, you'll have very big fractionation factor as well to -15. And that's why I think Shane put up values of very negative sulfur isotope signatures for cyanide-hosted gold deposits in Ontario. But if you precipitate pyrite from a fluid that's rich in H2S, you're not going to see that much fractionation. So when you have more positive signatures, it's more of a reduced auriferous fluid that's precipitating pyrite from a fluid rich in H2S. And when you have more negative signatures, you're precipitating pyrite generally from a fluid that might be more oxidized. So sulfur isotopes are a very good track of process. What's occurring to that fluid to precipitate gold? So if we think of gold, it's being carried. We know it's carried by bihydrogen sulfide complexes. What occurs to that complex to precipitate gold? Here we have a phase diagram. On the y-axis is oxygen fugacity of a fluid. On the x-axis is pH. We see gold solubility levels, so where it's most soluble in the fluid in darker yellow colors, and where it's least soluble in lighter yellow colors. We see the various species that are stable at those various conditions, so sulfate species and sulfide species, and we see the mineral buffering assemblages in black. So if we can see that if you oxidize a fluid, you quickly traverse through to sulfate and will destabilize these gold complexes and precipitate gold. So it's a very good process for precipitating gold, slightly oxidizing a fluid. And that corresponds to big changes in sulfur isotope space. So when you add oxygen to your fluid, you will change to your sulfur isotope signature to much more negative values. So sulfur isotopes are very sensitive to processes that are occurring. They're not as sensitive to the fluid source in that case. So what are processes that can happen in orogenic gold deposits? Well, we can have fluid mixing. These are various processes that have been hypothesized for various orogenic gold deposits to precipitate gold, and not every orogenic gold deposit has one mechanism of precipitating gold, and there could be various processes that are occurring at the same time. But some people have hypothesized that fluid mixing is really important, so a deep metamorphic or magmatic fluid that interacts with meteoric fluids or pore water in the upper crust to precipitate gold. We have clear evidence in some deposits, like at Kanawha Belle, where fluid pressure fluctuations result in phase separation of the fluid, whereby hydrogen is put into a volatile state. This oxidizes the fluid and precipitates sulfides and gold. So this happens especially in orogenic gold deposits that are closer to upper crustal levels. And there are many orogenic gold deposits where it's clear that fluid-rock interactions are really important. So sulfidation, if we see orogenic gold deposits hosted by banded iron formation, it's usually very clear that sulfidation plays a big role in releasing gold in that orogenic gold deposit. That's where H2S is removed from the fluid to interact with iron and precipitate sulfides and gold. And other fluid-rock interactions or reactions can be important as well. And these reactions can be either oxidizing or reducing for the fluid. So what we wanted to do 10 years ago, when I was young and in Australia, was look at monitoring sulfur isotope signatures through a paragenetic sequence. And so this is the Paulsens deposit in the Ashburton Basin in Australia. And we see that there's two generations of pyrite. Pyrite 1 that's homogeneous, pyrite 2 that surrounds pyrite 1 is inclusion rich. And you can't really see it here, sorry, but this is gold inclusions in pyrite 2. So what happens from pyrite 1 to pyrite 2 to precipitate gold? And can we monitor that in sulfur isotope space? And so we developed standards for sulfur isotope measurement by SIMS, and you have to, mount your little rock chips in a epoxy puck, get time on the SIMS. It's a long process, but you can get sulfur isotope data. But now, I want to show you what we've been doing at Université Laval to speed up this process and collect more data. So, at first, we started working on trying to understand sulfur isotope signatures in the Val d'Or camp with Mitchie Herzog, who looked at sulfur isotope signatures across various deposits, the Triangle, the Beaufort, Pascal's Gold Trend, Goldex, and others. And he was looking at the sulfur isotope signatures in these typical quartz carbonate tourmaline veins, where we see in these veins there's large aggregates of normally pyrite. And he interpreted, about 4 or 5 years ago, that there looked like there was usually inclusion-rich cores in these pyrites and more homogeneous rims. And these homogeneous rims could be associated with the same type of inclusions that we were shown before by Maxime. So these, gold-bearing, tellurium-rich inclusions. Gold can form calaverite, so gold, tellurium, silver. And bismuth is around, but bismuth is never complexed or attached or precipitated with gold. It's in these inclusions, but it's never truly associated with gold. Gold can also occur as native gold in kind of these homogeneous areas, or remobilized along late microfractures. And this is also published last year in June in Mineram Deposita, these textures that he observed in sulfur isotope signatures. Also has a metal earth number, so that's good. And so, but again, this was 4 or 5 years ago. I want to show you guys where we're at today with analyzing sulfide signatures, looking at their chemistry and adding sulfur isotopes. So now we're going to the Bonnefond deposit. This is work by François Xavier. He will be presenting at the SEG poster session, so please go see his poster on Tuesday, March 4th, 10 till 12. And he has, the typical Bonnefond deposit is here near the Pascal's Gold Trend, owned by Eldorado, Quebec. And he has the typical quartz carbonate tourmaline veins, and I'm showing you a pyrite in those quartz carbonate tourmaline veins. And the pyrite is carbon-coated, so sorry for the blue color. But we see again that it has complex zonation in reflected light. And Maxime showed us brilliantly what we can do with infrared imaging or infrared microscopy now. We can now better understand the paragenesis of those pyrites. And so exactly like he sees at Triangle, and we've all been working together at different deposits, we see many of the same. Across the Val d'Or camp, or district, we see many of the same signatures over and over again in the pyrite aggregates. So an early core that's overprinted by this oscillatory zoned hydrothermal domain in the pyrite, and then overprinted by some sort of dissolution, reprecipitation boundary of the grain. And now we can add our trace element maps on top of that. So this is a trace element map on our laser, looking at nickel concentrations. All these sulfides are trace element poor. We don't have refractory gold. We don't have lattice-bound arsenic in our pyrites. They're very trace element poor, but the trace elements do display the different zonations. So we have, an enriched nickel core surrounded by this oscillatory zone domain that's defined by the nickel and cobalt zonation. And then it's remobilized. Nickel can be remobilized to this dissolved and reprecipitated rim. And what's interesting, and I think Maxime showed this as well, is that in these sulfide grains, again, this is a pyrite, it's also carbon-coated, so this is gold here. Gold is circled here, these blue grains. we can see with the trace element mapping that gold is really associated with these dissolved grain boundaries. So whatever came in, whatever fluid came in, the day after QTC emplacement, 50 million years after QTC emplacement, I'm not sure, but whatever fluid came in to dissolve the pyrite and reprecipitate it, also reprecipitated gold at these reaction fronts. And we don't just see that at Bonfons. I wanted to highlight also an arsenopyrite-bearing deposit. So in the Val d'Or camp where QTC veins or QC veins are hosted in the Cadillac Formation, normally arsenopyrite is the main sulfide. And so Bruno Coldebella has been looking at the Ornata deposit. We see it here, a quartz carbonate vein hosted in the Wacky from the Cadillac Formation, and arsenopyrite aggregates. Again, arsenopyrite it hosts gold in the same habits. We don't have lattice-bound gold in these arsenopyrites, or not much of it anyways. We have mostly gold as gold tellurides or as free gold inclusions within these arsenopyrites, and they look just normal in reflected light, but when you map them for the trace element contents, we see that there's again this oscillatory zone domain here, defined by the cobalt zonation, and then it's all dissolved at its boundary and reprecipitated, and we see that that reprecipitation also affects gold in the grain as well. So gold is preferentially associated with this dissolved grain boundary, and so this is late, as Bruno was saying, late in the paragenesis. Whether gold was reintroduced at that time or remobilized, I think it's still not clear, but more work needed to figure that out. So, sulfur isotopes by LA-ICPMS. I hope I have a few minutes. Sorry, I'm a bit late. What we want to do now is not send our samples to Australia, like mount new samples and send them to Australia. We want in our basement to then collect sulfur isotope information on our LA-ICPMS, because we can throw 6 thin sections in our system at once and map them. So you can be doing your petrography, your reflected light petrography in the morning, and then your trace element maps in the afternoon, sulfur isotopes after that. And Guillaume Barret helped me set this up. We installed the system in 2018. 2020, we had renovations. CF installed in 2021. And then we developed reference materials and the analytical protocol in the past 2 years. So we had to develop reference materials. This takes a lot of time: chemical characterization, isotopic characterization. All you guys that say you just want your isotope analyses, the amount of time it takes to develop this is significant. Also, the analytical protocol. How do we optimize our system to collect sulfur isotope signatures? I think I'm running out of time. I was going to talk about the systematics of QQQ ICPMS, but just to highlight that we can better resolve interferences with a triple quad, and so we can separate the masses that we want to measure better. And then we did a lot of testing on the different analytical parameters to collect sulfur isotope signatures with the best analytical conditions possible to get the best results. And what we've come up with is we can have uncertainty of about plus or minus 0.5 per mil on delta 34S. So it's higher for sure than other methods, but generally we're not that concerned in sulfur isotope space if it's 3 per mil or 4 per mil. What we're interested in is observing a variation from one to another, which can help us understand processes that are involved. So we've been combining this. So just like I showed you, reflected light, infrared imaging or infrared microscopy, trace element mapping of sulfides at the triangle deposit, and then collecting sulfur isotopes on top of that. And another example, we have, this is actually an epithermal deposit in Peru, I think, but it's looking at pyrite, different types of pyrite, inclusion-rich, coliform, etc., mapping it for its trace element signature and adding sulfur isotopes on top of that to better understand processes. So I won't give results now. I think George is going to cover tomorrow afternoon a lot of the sulfur isotope and oxygen isotope results that we have tomorrow afternoon. But just to highlight that the goal is really to build sulfur isotope vectors. But these require big data sets, and we have to think of scale of sampling, spatial coverage, scale of analysis, what the texture of each sulfide grain represents, and we need to better understand how we can characterize background signatures and understand what controls changes to that background signature and how that's reflected in ore or gold precipitation. And so this is a goal, but we have to be able to collect sulfur isotopes much more quickly than we have in the past and build bigger data sets. And so this was the whole goal in completing LA sulfur isotopes by LA-ICPMS. I think you guys already saw from Shane and Shafak, I'm after them, but a lot of this will be applied in their postdocs over the next year or so. So thank you.